Thank you. Actually, it just occurred to me that it'd be interesting to know what streaming platform you were using for the hybrid stream of this, because that's really where this project comes from. Is I think I titled this talk something like "How Not to See the Goal Before You've Heard About It." So I don't know who else has had this happen to them. It happens to me a lot. You're watching a match, you might be watching streaming, and your friend's watching on cable, and your friend texts you, and they're like, "Hey, wasn't that a great goal?" And you're like, "Goal?" And so the question is, why is it that it lags so much? Typically, I don't know, I see maybe 30 seconds or a minute even of lag when I'm watching football over the internet. And yet we know we can do real time, right? Because we've all used WebEx, Zoom, Teams, etc. So we know that does. Oh, that reminds me. Yes, it is Zoom they're using. Yeah, so Zoom is real time. So why is it we can't stream the football real time? Well, it's hard, right? And why is it hard? It's hard because the scale you're trying to achieve. This isn't like one conference bridge with 50 people on or something. This is like you're streaming a match and 10 million people are watching it, and so you clearly can't have one big node in the middle of the internet spraying it out. You've got to have content distribution networks, etc. And today, content distribution networks are all based on the web, right? So it's basically web proxies. So I would connect to a web proxy, it would connect to the next one, it would connect to the next one, eventually the origin, and next thing you know, you've got 30 seconds of lag. So I guess my thesis is, in a cloud-native space, we can fix this, and we can fix it by building real-time into Kubernetes, or nearer to real-time into Kubernetes, and then deploying cloud-native content distribution using that. So, otherwise there's no clock on this, so somebody better wave at me if I'm going on too long. So my contention would be that Kubernetes was really built for web applications, and the challenge is going to be as we start to do real time. And so if you ever did an MBA, which I certainly didn't, you'll have discovered the joys of the 2x2 matrix. So pretty much any problem in the world, a consultant will tell you can be divided into a 2x2 matrix. So let's look at apps. So non-real time and real time, interactive, so that's where you have request-response semantics, or streaming, so that's pub-sub. And my contention would be that web apps are pretty squarely in that top left corner. And as an example, so on our booth over here, where we're showing something completely different, we have Kafka integration, for example, which is your classic streaming, but not real time. But really, it's real time where we're like, okay, so how do we do this in Kubernetes? There's I don't know if anyone here has come across Quilkin and Agones from Google for Games. They're focusing very much on the kind of online gaming space. What I'm presenting here is how we do real-time streaming media. So the complete opposite corner from web apps. So quick diversion into how video actually works, and this is my top-level view as someone who's a networking person, not a video person. So imagine, you're watching a football match online, there's a bunch of cameras at the stadium, there might be an outside broadcast trailer or something, so either they're going to pick one feed to send back to the studio, or they might send them all back. But at some point, you've got to mix it, you've got to decide, okay, this is the camera we want to be showing right now, and you're going to stick on like a little strip at the top saying, unfortunately, something like, Newcastle 5, Tottenham 0 after 20 minutes. Yeah, let's not go there. Where am I going with this? So you've got all that, and then you got to encode it, because ultimately those studio feeds are probably 4K HDR uncompressed. It's something like 12 gigabits per second, and clearly that's not going to get to my home. So depending on where you're watching, you've got to encode it either for CDN caches, but it might be being sent out to antenna head ends, to satellite networks, etc. And so in media, they tend to talk about the contribution network as this piece sort of from the camera all the way to once you've got it mixed, and then distribution, which is getting it out to the antennas and the caches. And then finally, of course, you have deliveries to users, and that's going to be specific to what technology you're using. As I say, for over the top, it's typically CDN caches sitting either sort of at the edge of the ISP network or deep within it. And so with media streaming mesh, what we're saying is that we ultimately, in time, we want to address all of this. Right now, I guess the focus is probably on things like encoding, because you think about that. I mean, traditionally, it's been hardware devices, but really, it's just compute workload. It's just number crunching. So that should be able to move into the cloud. And then distribution out to caches seems pretty easy to do as well. The contribution side gets some cool challenges. I don't know if anyone who's ever worked with that stuff, but if you've got 12 gigabits per second and you cannot drop a packet and you cannot jitter, it's an interesting challenge for Kubernetes. Delivery to users, I think the challenge is more the sort of, my TV's probably not getting a protocol upgrade anytime soon. So I think for a while, the final drop's going to always be HTTP-based streaming. So how does that HTTP-based streaming work today? Well, if you've ever looked at this from a sort of TCP dump or whatever, you will see that your browser makes a connection. So if it's unencrypted, it'll be port 80, HTTP. And what it gets from the playlist is effectively manifest, a little media playlist saying, here's a bunch of chunks. And those chunks are normally like a couple of seconds long. And so what will happen is your client will start playing those in. And the challenge is that if you're watching a film, then it's pretty easy because you can buffer up a whole ton of chunks before you start playing stuff. And so then if you start to get packet loss and things are getting delayed, you can shift down to a lower resolution or whatever. The challenge is going to be with live. That's the trade-off, is sort of reliability against delay. And sometimes what I'll see in my demo is the HTTP live streaming feed, if it drops a packet, literally the video will freeze, and then suddenly they'll be playing football at 3 times real time as it catches up. And yeah, you just repeat and repeat and repeat. So what about actual live video? So there's a couple of different approaches to this. The first one is exemplified by RTSP, which is what a typical security camera would run. So the client will connect to the camera. It'll basically ask for the media streams on a URL, so it gets that sent back from the camera. You might have one for audio, one for video, typically. But what you've now got to do is you've got to negotiate UDP ports for each of those streams, and this is the challenge, because you're now going to stream over UDP, but those UDP ports are going to be dynamically assigned, so you cannot know these ahead of time. So hold that thought in the back of your mind. Another approach is to use IP multicast. I don't know if anyone here has ever played with IP multicast. It's 1 or 2 nods to the head. In fact, this is if you were using, if you're on BT for your IPTV, that's effectively what it does. But there's a couple of different approaches. This one is that where you can have a set-top box and it will know the mapping from channels to multicast groups because the server's always sending. The other approach, and this is what you do in contribution video, is you'd have a controller just connects to the source and says, okay, again, the same sort of media information we saw on the last slide saying, well, what have you got? And then if you've got a receiver, so an encoder or whatever, it'd send that to there. The receiver then would join that multicast group and the traffic flows. But that sort of negotiations all kind of out of band in this case, rather than on a TCP channel directly between the 2 endpoints. So how do we do this in Kubernetes? Because that's what starts to get interesting, right? So the first approach I thought was, well, why don't we just use kubeproxy and node port and everything will be good? Turns out it's pretty good for TCP, HTTP, UDP apps. There's a bit of a thing with node port, of course, that it puts you on a nasty high port number, so you end up still wanting an ingress or something to put you on a good port number, which again, in my demo, that's what you'll see. But real-time media, no support, and it's back to those last 2 slides. So firstly, the first example with the RTSP channel, you had a TCP connection and you were negotiating UDP ports, and our kubeproxy is just a NAT. So as far as it's concerned, that's just a TCP connection, it's NATing, and it can't see what's going on inside it. So it has no way to see those UDP port negotiations, so that will break it. And what you'll see if you run RTSP through this is it will freeze for like 30 seconds. Eventually it gives up and it just tries with pure TCP with no UDP. The second example with multicast, well, most Kubernetes CNIs don't support it, so that's not going to work. So what about service meshes and load balancers? They're great for HTTP particularly, but again, today typically no UDP support, and when that comes, it'll probably come specifically in order to do HTTP version 3, which runs over QUIC, which runs over UDP. But again, no support for real-time media. And so, well, the next trick you could try is host networking. So basically, why don't you just run your media app and run it in the host network namespace, and then everything's going to be great, right? It all just works, because you've got no CNI, you've got no NAT. You've also only got 1 pod, because now you've only got 1 copy of each port on the server, because you're now in the server's own namespace. So if you want to expose that port 554 or whatever, say for RTSP, well, you've now exposed it, and you've used it, and you can't use it again. Also, probably a bit of a security issue. Do you really trust your apps to run in the host namespace? So that's really where we came from, media streaming mesh. We said, right, let's solve this. Let's build a control plane proxy that handles that first problem of the UDP port negotiation. And then let's build a data plane proxy that will actually carry its RTP, the real-time protocol that runs over UDP. So let's build that proxy, and that will then build this kind of fan out. So instead of having multicast, effectively have almost like an application layer multicast where you build a tree through your network, sort of node to node. And again, we can proxy the other stuff because we run over it. I think I stuck that one in orange because, well, we won't do HTTP, though we will do Quick. So this is the demo I'm about to show, so I'm rattling through it fast. And this also gives you a clue, some insight into what we're actually building. So you can see we have the control plane here. We have one per cluster because we want to minimize the footprint. We run a data plane on each node. So this is a daemon set. So there's the RTP proxy itself that gets programmed by the control plane. This stub thing's like a mini sidecar that we run alongside that does, in fact, you'll see what it does as we walk through this. So for example, the client connection, effectively, in this case, it acts like an ingress. It's going to pull out the control plane traffic, send it over gRPC into our control plane. We've used gRPC for everything. It's kind of neat, it's nicely modeled, and we can do things like failover easily rather than trying to mirror TCP connections. What you'll see in the demo is then it'll make a call to the Kubernetes API, and that is because the URL is going to have like a name on the end of it, and we'll look that up and we'll find a matching Kubernetes service. We'll then find an endpoint for that service, and then we'll connect to that. The thing I mentioned earlier about being able to stream all the video over TCP, we've actually implemented interworking for that. So inside the pod, we happily let it all come to us on TCP, but then we break it out over UDP. The proxies have been programmed by the control plane. That was the pulse. And then, so effectively, you'll send to your nearest one, because that's running on your host, and then you'll find out where the user is. It'll go to there, and then go back up. The cute thing about this, back to what I said about the fan out, is now if a second client joins and connects on the same node, it'll tell the control plane, and the control plane will just send it back out of the same one. So you can see now that the camera is not being hit multiple times. In this case, it's not really a camera because I put a fake video feed in the cluster. But if you think about it, you don't want your one security camera to be hit by 100 users who are all streaming video. You want to build that tree to minimize the impact. I should show the demo before I do that. So in Zoom, right, so how do I share? Right, so this is, so VLC is what we're streaming this on in real time. In fact, probably I just want to share the desktop, don't I? Because that's going to be easier. Yep, so hopefully there you can see this was a match that took place a couple of weeks ago where England's women proved they don't choke like the men. And they can actually win a penalty shootout. It's remarkable. Somewhere here, I was running, and this is HLS running from the same node. And what you'll see is it's some serious lag there. So the HLS is way behind that live feed. So she's about to take the penalty, and it hasn't even. This is still the end of the previous loop because I'm just running it on loop to make my life easier. So there, the goal's gone in. They're still celebrating the goal that happened. Oh, there you go. And so that's the challenge. I mean, this is just one hop of HTTP, but imagine now with the whole CDN how you easily get to that 30, 40 seconds of lag. So finally, in terms of where are we trying to get to with this? I mean, clearly, goal one is we can now run more than one pod running a media app in real time on the same node. That's sort of table stakes. Where we want to get beyond it is this top half is really all the same benefits you'd see from a service mesh. So, observability for us is not just knowing the topology of these trees, but also being able to measure the jitter and packet loss through them. Security in terms of SPIFFE for authentication, OPA for authorization, then doing encryption, node to node, probably just using RTP over Quick. By distribution, I just mean two things. One is building that optimal tree, but the other is, as well as measuring jitter and packet loss, you also want to minimize them. And so we're going to look to work with things like Intel's DPDK, which is a high-performance NIC driver, eBPF for stuff inside the node to get performance there. And then, I mentioned earlier, just trying to really optimize the footprint of the thing. And even support remote nodes that aren't part of the cluster. So for example, I was speaking to someone at KubeCon last week, and they can run containers on their security cameras. So why not literally run an instance of that data plane on a camera? Because there's nothing to stop us doing that and then accessing the remote control plane in the cloud. So that's the solution. As I say, fundamentally the goal is, to make sure that in future when we see the goal, we haven't already had a text from our mate telling us telling us it happened. It's all open source, so you can just get to it from the GitHub. The QR code will take you to our website, or you can contact me directly on any of those. The website also then has a link both to the GitHub and to our Slack channel. At this point, early stages, it's very much a prototype. You might have seen a bit glitching in that video. My next job after tomorrow is to rewrite the data plane. The stub is already written in Rust. The data plane is currently Golang, and I need to move that to Rust because I just need to get the performance there. But yeah, I've got a longer session tomorrow, I think, at 11:45, if I'm right. And what I'll probably do with that is run it more as a Q&A. So forget the slides, just ask questions, because this is a bit different to everything else in Kubernetes today. And probably through answering the questions, I can actually explain how it really works under the covers. But yeah, do come and talk to us. I'm here the rest of today and tomorrow. So I think that's my time.